right, let's finish up chapter 6, and then we'll be done with this stuff, talking about functions and relations. So, the last time in 6.5, I guess what I'm going to do is I'm kind of finish up what 6.5 was doing and then get into sort of talking more about 6.6. But at the end of 6.5, something that happens is we have we have functions that are injective and surjective. Basically, if a function is one-to-one, right? If it's one-to-one and onto, we call the function a bijection. So some really interesting properties about bijective functions are, well, one, that inverse functions exist for bijections, because, notice, I can always restrict a function so that it's an onto function, right? If you remember, in the chapter, it makes a comment about a function is always onto its range. So basically, if I just look at the range of the function, I can always say, well, that's my codomain, right? I can always restrict it such that that's what I get. So no problem there. But it's not always true that functions are one-to-one, right? So when a function is one-to-one, right, remember I can always take an element out of the range there, right, or out of the codomain, however you want to think about it, right? I can always take one element there and then find another element, right, that's a unique element in the domain, right? So each image element has a unique pre-image element, and so we can always find an inverse, right, map between the sets. So that's one thing, right? So if I have a function f, right, then I can find a function g such that, the composition of g and f, right, gives me an identity function, right? Basically, that when I compose g and f together, right, when I take g compose f, what I get is just, whatever comes out. So if I do g of f of x, right, it'll just give me the value x over here. Now something kind of nice is that if we have a bijection, like if it's truly a bijection, and we haven't had to do anything, we'll talk about what we do in 6.6, right? That I can actually find both a left and a right inverse so that, g of f of x or something is equal to f of g of x or some such thing, right? So that g compose f is equal to f compose g. So I can find both the left and right inverse for this, right? I'll call this g1, and I'll call this other inverse g2. So I have the left and right inverses for the function, right? And these just give me the identity map, right? Where it takes something to itself. Now, something kind of interesting is that, we can define all kinds of functions that turn out to be bijections. There's a very cool function at the end of 6.5 that's a bijection, and it looks something like this. So what I want to do is I want to create a function f that goes from the naturals to some new set, right, called the integers, right? So this is my domain, this is my codomain. What I want to do is I want to define it such that, right, f of x is maybe the best curly bracket I've ever drawn on here. Then I take x over 2, right? This is what I do if x is even. Right? And then what I'll do is negative x minus 1 over 2 if x is odd. So this is kind of an interesting function. It turns out that this is actually also a bijection. I won't prove it. The proof is in the book. You're welcome to read that this is actually a bijection. Proving something is a bijection is no more complicated than proving that it's both one-to-one and onto, right? Meaning that you need to prove that it's both surjective and it's injective, right? Or I guess injective and surjective is injective is. Doesn't really matter. It doesn't really matter, I guess, what order you prove them in. It could be one-to-one and onto, or then onto and one-to-one. Doesn't matter. But you can show actually that this function gives you the results, right, that you want. And so this is kind of a neat. This is kind of a neat function. So you notice that what's going to happen here, right? We're assuming that for the natural numbers we actually don't, that we won't start at 0. Right, so in this case our construction of the natural numbers is just the set 1, 2, 3, and so on. Well, I guess I shouldn't have written in brackets, but you get the idea. Right. Okay. So there we go. This is kind of an interesting construction, and if you're able to work through the problem, right? If you didn't read it, just see if you can see how it's bijective, right? So something that's nice about bijective functions is that if a function is one-to-one and it's also onto, what that means is the sets that I'm actually looking at are the same, right? So this means that in the set of natural numbers and z, right, they have the same what's called cardinality, right? We can think about it as that n and z are the same size. And I'll put size in quotes. Right, because really the size of these is both infinite, and it seems kind of weird because the natural numbers, it seems like they would have half as many numbers as the integers, but if I can find a bijection between two sets, right, this is actually not the only bijective map I could find between sets. I'm sure there's other bijective maps I could find between the sets. But, if I find a way, you can see it in kind of the small case, right? If I had a set, maybe 1, 2, 3, and I have another set, A, B, C, right? I can find a map right here. Right. Now, this is an easily defined map, right? So 1 goes to A, 2 goes to B, 3 goes to C, right? So notice that the codomain, I completely cover the codomain, right? Because it's an onto function. And also every domain element maps to a unique codomain element. I guess each codomain element has a unique pre-image element over here in the domain. So the mapping is unique, right? So each thing is paired up with just one other thing. Also, it's interesting that, I've covered it completely. So that means that the set here and the set over here, the set 1, 2, 3, and the set ABC are the same, right, say size, sometimes called cardinality, right? It's kind of interesting when we talk about the the naturals and the integers because they're both of infinite size. So it means that in some way that the infinite size that they are is the same. This is actually referred to as countably infinite. You can see something like that later on I think in the exercises if you want. There's a thing about Cantor's argument for this. And another thing that actually happens is that if I can't find, right, if there's no bijective map between the two sets, that means that they're actually of different size. So something that else that's interesting is that I have this infinite size set in natural numbers, but could I find a function f from the natural numbers to the real numbers that's also a bijection? Could I find a bijective mapping between the naturals and the reals? And it turns out I can't. Maybe we'll talk about this at some point later, but you can look it up. Cantor did what's called a diagonalization argument, and it's pretty interesting, right? But even though this is of infinite size, and we know that there are infinitely many real numbers, these are different sort of sizes of infinity. So that's kind of cool. So let's talk about some more functions. Sometimes it turns out that when I have a function, I can actually do some type of restriction in a way that allows me to get a one-to-one mapping. Because, really, a lot of times what I want, well, one of the things I want with a one-to-one mapping between sets is I want this invertibility property, right? I want to find inverse functions that take me from, I don't know, a range set back to some set in the domain, right? And sometimes it turns out that we can actually restrict our domain in a way that allows us to do a one-to-one mapping, right? So we can still maybe have everything in the range that we want, yeah? And I think that one of the canonical examples is the x squared function. So x squared looks like this, right? And we also have this thing we could do, right? If I actually don't allow this over here, if I say just restrict my domain to this, right, what I'll get is a function that looks like this, right? So if I let D, my domain of the function, be the set, well, I guess I'll just say, I'm not going to even write this way. Maybe I could just let D be all, right, we'll say non-negative real numbers. Right, so non-negative real numbers. So basically 0 to infinity, right, if you like this notation better. So if this is my domain, right, I've just restricted my domain in this way, right? So I'm not allowing any negative numbers. What I'll get is this very nice function. And similarly, right, if I restrict it the other way, so if I just allow negative numbers, well, some non-positive numbers, right, what I'll get is this kind of weird-looking function like that, right? And the mapping from here to here, right, from this set sort of to this set in a way, or from here to here, right, this is a one-to-one mapping, right, and it's also onto, we could think. It doesn't really matter. So in some ways, what I can do is actually get a one-to-one function. I can get a bijective function between the sets that I want, right? Just by restricting it, right? So you know that f of x is x squared, and if I'm restricting it such that I'm looking at only non-negative real values, then we could say our f inverse of x in this case is square root of x. We introduce this kind of notation here. If I have f, I can say f like this with d. This just means that I'm restricting it to this particular domain, right? What they're saying is that the domain restriction makes it such that I have, right, so the sets that I'm looking at are the sets of all x and y, right, such that x is in D, right, and x comma y is in F. So notice this F right here is actually an unrestricted F, right? But since I'm restricting the domain D, I'm only looking at the ordered pairs x, y from the we'll say from F, right? Sort of the, well, all of the ordered pairs that it maps to, but where x is in my restricted domain, right? So if we think about this function f of x squared, right, I would look at all of the things where it's all of the ordered pairs x comma x squared, such that, remember, x is going to be a non-negative real number, and x comma x squared are members of any of this thing, right? So if we're looking at that, something like 2, 4 would be in there, but negative 2, 4 is not going to be in there, right? Because notice that 2, 4 and negative 2, 4 meet both of the condition, or I'm sorry, 2, 4 meet both of the conditions here, but negative 2, 4 actually fails the first condition of x being in my restricted domain D. The other example is the sine function, right? So you've seen a sine function before. It's going to look something like this. Alright, so the sine comes like this, and then it does this thing here, not drawn to scale, obviously, so on, right? And we'll say that, oh my goodness. So here we've got like negative pi over 2 approximately. This is positive pi over 2. Well, notice if I take any value, c, and we'll pretend that this is positive 1 and this is a negative 1 over here, just so we get, I mean, even though this is a very crudely drawn picture of a sine function, but you know what a sine function looks like. Notice that here I've got pi, this would be like 3 pi over 2, this would be negative pi, 3 pi over 2, and so on and so on. So if I choose a number, right, any number between negative 1 and 1, and I draw like a horizontal line, this is definitely failing that horizontal line test we talked about, right? So it's definitely not a one-to-one function. But, I mean, if you've taken a trig class, or you've taken pre-calculus, or calculus, or whatever, right, you know that there exists something called an inverse sine function, sometimes called an arcsine. But on a calculator you can find it, right? So you can find something, right? You have like a sine x button, and you also have a little button that looks like this, or something, right? So I can find an inverse sine function. Now, something you'll remember is that when you were doing stuff, like say looking at a unit circle, well, we can keep turning around that unit circle, right? And really the same thing is going on here. I can kind of keep going on forever in either direction, right? I can keep going as far as I want. But sometimes when we want to solve an inverse problem, we actually don't get things on the entire unit circle. Because, the unit circle goes from like 0 to 2 pi, but if I actually allowed the sine function to range from 0 to 2 pi, and I mean, we can keep going around infinitely many times if we want, and go to as many pi as we want. So 0 to 2k pi, each k is an extra rotation. But what I could actually do is I could restrict my domain such that I still get the full range, right? But I'll make my function actually one-to-one, right? So if I let d be actually, you know what? I'll write it this way. If I let d range from negative pi over 2 to pi over 2, right? Notice that if I can define the domain here, right, I'll say my range, that's just going to be, it's still going to be negative 1 to 1. Right? So notice in this case, I can define sine, right, but restrict it to d, right, my domain. And in this case, I can actually find an inverse, right? I can find a function g that allows me to map backwards, right? And that's the sine inverse function. So I could take any number from negative 1 to 1, right? I could take any number from negative 1 to 1, and I can find, what the sort of inverse value is, right? So, like, notice here at negative 1, right, that's like negative pi over 2, right? At positive 1, that's going to be a pi over 2, right? Now, right, does it mean that pi over 2 is the answer for any possible 1, right? No, I mean, we have to be kind of smart if we're looking for other potential values, right? So notice that this actually gives us 1, but if we're out here and this gives us negative 1, but pi over 2, and then I've got this like 3 pi over 2 is also negative 1, right? And so on and so on. Now, restricting it from negative pi over 2 to pi over 2 is perfectly fine. I mean, certainly I could have restricted it from pi over 2 to 3 pi over 2. I could restrict it in any way that gives me 1 to 1, right? So you just want to make sure it's on an interval that gives you 1 to 1 mapping, right? And that's how we kind of restrict the domain, right, for this. And, it's still going to give us our full range of everything, and we'll still have mappings between something else, right? So this is a way we actually get around, this is the way we get around some kind of tricky issues. Because, we want an inverse function. We want to make sure that f is 1 to 1, and if we can guarantee that f is 1 to 1, I can always find a suitable inverse, or at least an inverse that will take things from that range or codomain and then map them 1 to 1 back onto the domain. Okay. Talk about a few more things. The book brings up something called a projective mapping, right? So pi 1 of x, y, that's just going to give me the value x, pi 2 of xy is always going to give me y. That's not particularly interesting mapping, but it is a thing. One thing you could imagine is that if I have an ordered pair xy in the plane, right? Like, let's say I've got this point, right? This ordered pair x comma y. Right? Well, what it's going to do is it's going to take this point xy and it's just going to project it directly down onto this, right? And I'll get the value x right there. And likewise with the, this point under the pi 2 mapping, it's going to just take it to the point y. It basically just returns the, the specified index given here. So 1 means it's going to return the first value, 2 just means it's going to return the second value, and so on. Here they find what's called a diagonal mapping that actually takes this and gives you, well, an inverse, right? We can find a function d that when I take d pi, let's say 1 of x comma y, well, it's not going to give me x, y back, because notice d, because notice that what's going to happen is this pi 1 is going to give me an x, right? So this is really going to give me d of x, and so what I'm going to get back is x comma x, right? I won't necessarily get back the original thing, but what I would get back is this. So I could actually just restrict my domain if I really wanted to a particular line on the, right? If I restrict my domain of the projection function to the line x equal y or y equal x or something, right? This is going to give me this particular thing here. So this is the domain. I'm only looking at this line. It's supposed to pass through 0, right? 0, 0. But if I did this, right, I could make the mapping bijective, right? I just restrict the domain of my of r cross r, right, to this specific subset of the domain that's just the line x equal y. So it'd be the set of all x, y, such that x is equal to y. And it would just look like that line. It would just look like a line that's 45 degree. It's a 45 degree angle, right? This y equal x line or x equal y line, whatever you want to think of it. So in this case, what I would get is I would get a bijective mapping from this projective map to, I could find this inverse. All right. I think the other thing that's brought up in this chapter is characteristic functions, and then some funny bracket notation. Characteristic functions are kind of interesting because if we let a function, I think they use like a 1 or something like that. Sometimes you see characteristic functions use this. This is called a chi. Right, so if I have a characteristic function of some set, right, S, right, what I could do is, let me see. So if I let S be some set, right, then we could consider S to be some subset of some bigger set, I don't know, A. And if I wanted to let, I could define my characteristic function this way. So my characteristic function of, let's say, my A's would be if, right, it's going to be, man, I cannot write this. It's going to be this. It's going to return 1 if A is in S, and it'll return 0 basically if A is not in S. So for everything else. Now they ask you a kind of interesting question, like how would you do for the complement, right, of S? So basically you would just switch this around, or you could think of it as that it'd be 0, right? You could just like kind of have this, I'll call it chi bar of A, right? It's going to be 0 if A is in S, and it's going to be 1 if A is not in S. And notice that this would actually give you the complement, the complement characteristic function, right? So the characteristic functions are always mappings where the codomain is 0 and 1. Right. So notice here what I'm doing is I'm defining a function, I'm calling it chi, and it's going from my set A to this set 0, 1. Right? And so if A happens to be a member of this, this set S, then I'll write a 1, otherwise I won't. So one thing I could do, like let's just do a small example. So let's I'll define S in this case, my subset. I'll define my subset to be the set 1, 2, right? And I could define another set A, right? That's sort of the superset. I could make it 1, 2, 3, 5. Well, notice that if I put 1 in, I'll get 1. If I put 2 in, I'll get 1. Right? If I put 3 in, I'll get 0. And if I put 5 in, I'll get 0. Right? So I get 1, 1, 0, 0, right? Because remember, all I'm saying is that is 1 in the subset S? Yes, it is. Then I put a 1. Is 2 in the subset S? Yes, it is. I put a 1. Is 3 in the subset S? No, it's not. So I put a 0, and so on. Right? The last thing I'll talk about is something called an Iverson bracket. It's kind of talked about at the very end, and it's of some importance, but not something I would say spend too many sleepless nights worrying about the Iverson bracket. If I have an open sentence, let's call it P of X, right? Then I can define this bracket function, right? These brackets, these are called the Iverson brackets. And what I do is I basically put my open sentence inside of that, and I can think of this as a sort of function, a sort of characteristic function in a way. It's going to give me basically 1 if P of X is true, and it will get me 0 otherwise, right? So if it's not true. And notice we can stick anything in here, right? An example they actually give is this. If I take I equal 1 to 24, and I do the Iverson bracket for 2 divides I. Well, if if I think about it, what does it actually give me? If I start at 1, right, I'm going to get 0, right? Because it's sort of a thing where I ask myself, does 2 divide 1? No, it doesn't. Right? Does 2 divide 2? Yes. Does it divide 3? No. Does it divide 4? Yes. And so on. Right? So what I'll get is just a bunch of zeros and ones, and I'm going to add them up. So the Iverson bracket's allowing me to count, right? It's giving me a systematic way of actually counting the number of even numbers between 1 and 24. Okay. And they also introduced this, they have another one, right? Equal 1, 24, right? And this is 3, so this is all, basically it's counting the multiples of 3, right? So here, right, remember we're going to get something like, that's 0, because 3 doesn't divide 1, 3 doesn't divide 2, it certainly divides itself, doesn't divide 4, doesn't divide 5, does divide 6, and then so on. Right? And then they give this kind of interesting one. So something that it's actually giving us is 2, right? Things that are divisible by 2 plus things that are divisible by 3 minus the things that are divisible by 6. So notice that what it's doing is it's giving us the things where 2 and 3 are unique divisors and 6 is not, right? So certainly 2 is going to give us this, right? 3 will be in this, right? Will be counted. But 6 won't be counted, right? 4 is going to be counted, right? 8 will be counted, right? Because that's an even number, but it's not divisible by both 3 and 2, right? So this is kind of an interesting thing I can do, right? It gives me a systematic way of actually counting some sort of divisibility principles, right? By using what's called the Iverson bracket. Right, so all I do is I stick an open sentence in there, and it's going to return a 0 or 1 based on the truth of that statement. So it's 1 if it's a true statement, right? If what comes back is false, then I get a 0. All right, that's it.